I want to talk about chemical shifts in the proton NMR, and we're going to look at some common NMR shifts that you should be familiar with that tell you that there's certain structures in the molecule, as well as looking at certain things that influence the position of the chemical shift, moving it in one direction or another. We're going to start off by looking at this NMR spectrum, and this is the NMR spectrum for cyclohexane. And you'll notice that cyclohexane only has CH2 groups in it, and we get one nice peak at about 1.3 ppm. And we're going to use this as our reference to compare other CH2 groups to see what happens when we put other substituents in the molecule. And I want to remind you that all of the chemical shifts that we report in the proton NMR are relative to the external standard TMS, tetramethylsilane, which is not shown in this NMR spectrum, but I've kind of drawn in here, and that's assigned the value of 0 as the reference. I want to look at a few other NMR spectra that are from compounds with a little bit more diversity in them than cyclohexane and see what happens to our chemical shifts. Looking at this NMR spectrum, it is for 2-methylbutane, and I want to remind you that our CH2 reference, when we have nothing else affecting it, should be at about 1.3 ppm. And I've marked the approximate position of that with the red line that I've drawn in the spectrum. What I want to do now is assign the positions of the peaks from the different groups in my molecule so we can compare that to our CH2 reference. First, if we look at our 3 methyl groups, 2 of them are equivalent to one another, and the third is not. All of them, both the two equivalent ones and the one non-equivalent one, show up at about the same position, at about 0.9 ppm. Next, we have our methine hydrogen, which I've labeled C, and that shows up a little bit further downfield than the CH2 groups at about 1.6 or so. And finally, we have our CH2, which we've assigned previously. I'll label it D here. And it is at the position we mentioned before, 1.3. So we can see that methyl groups, CH3 groups, are a little bit further upfield than a CH2, where the methine, the CH, is a little bit further downfield. And these values that we've tabulated here, 1.3 for a CH2, 0.9 for a CH3, and 1.6 for a CH, are useful references, and we can compare these to what happens when we take our unsubstituted alkane, or our alkane hydrocarbon that has no other non-carbon hydrogen groups in it, and compare this to the chemical shifts for these same groups when we start substituting other things into the molecule. And we're going to look at that right now. In general, not universally, but in general, most of our substituents will move the signals further downfield. Usually an electron withdrawing substituent moves our signals further downfield, and we'll see that in a minute. I want to look next at this NMR spectrum, which is the NMR spectrum for 2-butanol, and I want to assign the peaks in the spectrum to the corresponding hydrogens in my structure. If we do that, this is what we get. And I want to look at what effect having my OH group in this molecule has on the chemical shift of the various groups here. And I'm going to start with A, the methyl group at the far end of the molecule. And we said before that a methyl group should show up at about 0.9 ppm. And if we look, it does indeed show up at about 0.9 ppm. So there's no change to the chemical shift. And I'm just going to label that with an NC for no change. And this makes sense because the CH3 is several carbons away from the OH. and the OH doesn't really affect it that much. If we look, on the other hand, at the next CH3 group, the one that's a little bit closer, one carbon closer to the OH, it does affect it a little bit. And it shifts it by about 0.3 ppm downfield. I want to look next at the CH2 on the other side of my alcohol group. And again, you'll see that we do shift the peak a little bit downfield by about the same amount as we shifted the CH3. I'm going to say maybe we shifted it 0.2 this time. Again, when the CH2 is one removed from the COH group, it has a little effect, not a dramatic effect. On the other hand, if we look at our methine hydrogen, our CH, that's attached directly to the OH, we said from our previous example that that should show up at 1.6. It's now a little bit over 3.6. So this changed the chemical shift dramatically by about 2 ppm. And this is a general trend we will observe as well. Having a group distant from a polar functional group like OH, this CH3, for instance, will have minimal effect. As we get closer, so going from the CH3 down the end to the CH2, that's one carbon away, we get a more significant effect. And when the group is directly attached, like the CH labeled C, we're going to have our most dramatic effect. There are a few other functional groups I want to discuss, because these are chemical shifts that you definitely should recognize. In particular, I want to point out that anytime we have a peak between about 6.8 and 8.0 or so, that's a really good indication that we have an aromatic ring in our molecule. So in this NMR spectrum, the peaks from our benzene ring, our aromatic ring, are showing up at just over 7. And our CH2, which we previously said when it is unaffected by other groups, should be at about 1.3. This time, because it's directly attached to the benzene ring, is at about 2.6. So it's been shifted by about 1.3. On the other hand, the methyl group, which is not directly attached to the benzene ring, in which we would expect to have a smaller, to be affected to a smaller degree because it's not directly on the benzene ring, has shifted a little bit. It's down at about 1.2 or so, and we said previously if it weren't affected by anything, it would be at 0.9. But it's not as much as the group that's directly on the benzene ring. So it's been shifted by about 0.. If we switch from aromatic compounds to an alkene, like the hexene shown here, you'll notice that the hydrogens on the double bond are further downfield, but not quite as far downfield as for an aromatic ring. The hydrogens on an alkene are generally going to be between about 4.5 and about 6.5 or so. You'll also notice that the one CH2 group that's closest to the alkene has its chemical shift moved about 1 ppm further downfield, but the other groups that are further away aren't really affected that much. Two other functional groups I want to mention. First, anytime you have an aldehyde, you generally have a peak between 9 and 10. So this peak at about 9.6 is from the aldehydic hydrogen. And finally, any hydrogen above 11 for the stuff that we're going to be dealing with this semester is usually from a hydrogen on a carboxylic acid, the carboxylic acidic hydrogen. There are more detailed chemical shift charts that you can and will consult during the course of the semester. We don't have time to go through the details of those charts today, but I did want to highlight some important chemical shifts that you should know.